Hey there, Calc 2 crew, and welcome back to the Daily Problem Sets. Hey, today we're going to be taking a look at section 11.3. We're going to start by talking about the integral test and the p-series test. And I really like the integral test for testing if a series is convergent or divergent, because I think not only is it very intuitive, but I think it's also a lot of fun. So let's talk about the integral test right now. Say, suppose the function f is a continuous positive decreasing function on the interval from 1 to infinity, and let a sub n be equal to f evaluated at n. In the series, the sum from n equals 1 to infinity of a sub n is convergent if and only if the improper integral, that's the integral from 1 to infinity, of f of x dx is convergent. In other words, if the improper integral is convergent, then the corresponding series is convergent, or if the improper integral is divergent, then the corresponding series is divergent. And along with this, actually you can show this result from the integral test. You have the p-series test, which is going to be very quick. We love p-series, we love geometric series, similarly. But for the p-series test, we say the p-series, the sum from n equals 1 to infinity of 1 divided by n to the power of p, is convergent if p is greater than 1 and divergent if p is less than or equal to 1. And so again, remember you should have already watched the lecture video before taking a look at our problem sets, but let's take a look at them together. I want to use the integral test to determine whether or not the series is convergent, and here I have the sum from n equals 1 to infinity of n divided by n squared plus 8. So now what I want to do right away is I want to try to model from this, I want to model some function of continuous variable x. And it's no big surprise where that function comes from. So let me write it down. It's going to be the function f of x is x divided by x squared plus 8. Can you notice the similarities? I'm replacing that discrete variable n with continuous variable x. And this is going to be on now the continuous interval from 1 to infinity. Instead of just making those discrete stops along the way, we're going to say the interval starting at 1, including 1, and then to infinity. And I want to try to argue that this function is positive, continuous, and decreasing on this interval. Now first, we can talk about that this function is positive. And we'd like to provide some type of justification for our instructor, whoever is sort of judging our work. But let me just sort of speak to you about it instead of writing it down. And it'll be your job to write down what you think is good justification here. Notice that we're only picking x values from an interval where x is positive. It's either 1 or greater. So x is positive, so that means the numerator is positive. And x squared is going to be positive, and it can't be 0 since x isn't allowed to be 0. So x squared is positive, and then adding 8 to it stays positive. We have something positive divided by something positive. The ratio of positive things gives us a positive quotient. So we are positive on the interval. What about continuity? Are we continuous with our function on the interval from 1 to infinity? Well, a rational function only has an issue when we have division by 0. Well, I should clarify, I don't have anything like any root functions inside of the rational function or other pieces to it. I just have, algebraic terms only. So we'd say it's the division by 0 that we're worried about, but there's no way that I can get x squared plus 8 is equal to 0, right? I can't get x squared to be equal to negative 8, not in the real number system. So there's no division by 0. There's no threat then for the entirety of the function, so it is continuous. But now I want to know, is this decreasing? Now to figure out if the function is decreasing, and I'm a bit old-fashioned, I would work with the derivative. So let's find f prime of x. Let's do it. If I take the derivative, and I'm going to use quotient rule, so I'll say, let me write the old denominator up on top, x squared plus 8, times the derivative of the numerator, which is 1, and then minus. Now I'm going to rewrite the numerator, which is x, times the derivative of the denominator, which is 2x. And this is all divided by the old denominator squared, so x squared plus 8 quantity squared. And if I clean this up, See, well, here in the numerator, I have x squared plus 8 times 1 is x squared plus 8, and then minus 2x squared, and then divided by x squared plus 8 quantity squared. And then I can just clean this up a teeny bit more. Say that this is going to give me 8 minus x squared, if I combine those like terms, divided by x squared plus 8 quantity squared. There's my derivative. Now, notice the denominator is always going to be positive. It's x squared plus 8, and then I'm squaring it on top of that, adding insult to injury. But if I want to find out then if the derivative is going to be negative, then it's really the numerator that dictates the sign. So we'll say f prime of x is negative. Remember, if the derivative is negative, the original function is decreasing. So f prime of x is negative when 8 minus x squared is negative, which means less than 0, right? And when does this happen? Well, let's solve for it. If I add x squared over, we'd say 8 is less than x squared. And I like my variable to show up first, so I'm going to write this as x squared and then 8. And I just have to make sure my inequality is still pointing and facing in the same directions. So x squared greater than 8. And then if I take square roots, I'd say, well, then x has to be greater than the square root of 8. And what is this? Well, it's a little bit less than 3. I think it winds up being about 2.8-ish. So we're saying, okay, so this means that my function f of x is decreasing, but it's decreasing when x is greater than about 2.8. Don't make fun of me in the comments. This isn't the exact value, but it gives me a rough idea. So this is actually interesting. My function isn't always decreasing. In fact, it looks like it starts increasing a bit and then decreases very shortly thereafter and decreases forever from then on. But it doesn't always start out that way. So what we can say about this, we can say that the function, it's not decreasing, but it is what we would call eventually monotonic decreasing. It's eventually decreasing. And that's actually enough for what we're trying to do. So we could say that, this is decreasing on the interval from, so we'd say decreasing, I'll write it instead of just saying it, decreasing on the interval from square root of 8 to infinity. But if I think about what this means in terms of the series, we would say, well, this means we're decreasing on n equals 3, 4, 5, so on and so forth. And why is it okay to just have eventually decreasing for the integral test? Why is it not so strict? Well, think of it this way. I had the sum that I was starting with, and it was from n equals 1 to infinity. I'll just write a sub n, but we remember what it was. It was this n over n squared plus 8. And instead of having it from n equals 1 to infinity, I could say, well, what about n equals 1 to 2? And then plus, now I can take a look at from n equals 3 to infinity for the rest of it. This piece here, from 3 to infinity, I can use integral test on this. I have those three sort of things I have to check first. So I should be able to work with, I have those three conditions. So I should be able to do integral test on this. And if this is convergent, then adding 2 terms to it isn't going to ruin the convergence. It won't. This isn't going to make it diverge, is what I'm trying to say. This is a finite sum. If I tell you to add 2 things, there's no way it's going to diverge. So this is safe, no matter what. This isn't going to dictate the behavior. This is convergent, no matter what. It's the infinite series that we want to know about. Is this convergent? Is this divergent? This is going to call the shots for us. So it's certainly fine for this to be eventually decreasing, so long as at some point the function starts decreasing and doesn't stop decreasing. So we're good to go with the conditions here. We say it is positive, it is continuous, and it is that eventually decreasing. So now I want to take a look at the improper integral. I want to do integral tests now. So we'll say, yeah, let's take a look at the integral from 1 to infinity of x divided by x squared plus 8 dx. And right away, we don't like improper integrals to stay improper. We want them to be limits as proper integrals. So we say limit as b goes to infinity, the integral from 1 to b of x over x squared plus 8 dx. Now I want to integrate this. And to integrate this, I really would want to work with a substitution method. So I'm going to do my work here to the side. I'm going to say notice. Let me just write the generic integration out. And we'd say, well, let u be equal to x squared plus 8. We're doing u sub. The derivative du gives me 2x dx. I see my x dx. So we'll divide both sides by 2, multiply by 1/2 is what I mean. 1/2 du equals x dx. And this transforms into the integral of 1/2 times 1 over u du, which we integrate to get 1/2 natural log absolute value of u plus a constant c if it's just this unbounded improper integral. And then I'd back substitute to get 1/2 natural log absolute value of x squared plus 8 plus c. Now I don't need the constant plus c because I have a bounded integral. It's coming from my improper integral. But I'm going to use this result. It almost looks like I did sort of a bit of a detour here by happenstance, but this is relevant because this is what I'm trying to integrate. So we'll say, okay, limit as b goes to infinity of, and now here I have 1/2 natural log absolute value of x squared plus 8. I don't need the constant since I'm bounded, and that's from 1 to b. And now I want to do the evaluation, right? Fundamental theorem of calculus part 2, electric boogaloo. Plug in the upper bound, plug in the lower bound. I'm going to leave 1/2 as a coefficient, but then I'm going to plug in my upper bound of b, so that's natural log of b squared plus 8. And then minus, I'll plug in 1, natural log of 1 squared plus 8. I'll clean this up as much as I can before having to take a look at the limit. I can't do anything with natural log of b squared plus 8, but here I have minus natural log of 9. And now I can talk about what I'm going to get for the limit. Now there's some important stuff to mention here, and I'll do that sort of to the side. We'll say, well, the limit as x goes to infinity of natural log of x is infinity, that the natural log function is actually unbounded. It's a slow growth. It's kind of almost unbelievable that natural log is unbounded, but if you don't keep natural log in check, if nothing is there to stop it, if nothing intervenes, it's going to very slowly, just like watching paint dry, it is going to head to infinity. You know, it's that tortoise and the hare kind of story. You know, that determined, we should all want to be as determined, but also as relaxed as the log function, natural log, is. It's headed to infinity, but it's got nothing to prove on the way there, that's for sure. But so now we can use this to help us out with what's happening. So what we're saying is, and sort of pardon my poor notation, this term here is headed to infinity, right? So we're saying, okay, infinity minus a number, still infinite. You know, infinity divided by 2, still infinite. So all of this limit is bringing me to infinity. So I'll say, okay, so this is infinite, which means that the improper integral diverges. Since my improper integral is divergent, the same result is true of the series. So we'll say then the sum from n equals 1 to infinity of n over n squared plus 8 is also divergent by integral test. We always want to give a shout out to the test that we're using. If you don't want to say, you know, by integral test, you could always use a hashtag. We could say hashtag divergent, hashtag integral test. We want to give a shout out to the test we're using. Definitely. But so that's our first example of integral test. Let's take a look at another example. Determine whether or not the series is convergent or divergent. And here I have 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125 plus so on and so forth. And there's something worth noticing here. I think it's even more noticeable as we get further out. But 1 over 125 is 5 times 5 times 5, or that's 5 cubed. 1 over 64 is 4 times 4 times 4, which is 4 cubed. 1 over 27 is 3 times 3 times 3, which is 3 cubed. 1 over 8, we know 8 is 2 cubed. And 1, I could actually, if I want to, I could write this as 1 over 1 cubed. It's not incorrect, it's true. So if I notice this pattern right away, I could say, well, I don't want to have this maybe left as just all of the addends written out and then the dot, dot, dot showing that it goes on forever. I can now write this in a closed form, saying, well, this is the sum from n equals 1 to infinity of 1 divided by, everything's got a 1 on top, and then it's n to the power of 3 as we go through those different values for n. But right away, as soon as I write it this way, I want you to notice this is a p-series. I remember we talked about the p-series before. We said that was the sum of 1 over n to the power of p. This is a p-series. And it's a p-series with p equals 3. Now remember, what do we need for this to be convergent? We need p to be greater than 1. So I can flip back up to it and go past the work that we've done. It says this p-series is convergent if p is greater than 1 and is divergent if p is equal to 1 or if p is smaller than 1 for that 1 over n to the p. Since p is equal to 3, which is greater than 1, we have a convergent p-series. And it's just that quick to justify if we can notice something is a p-series, which is why, and I mentioned this at the beginning of the video, what do we love? We love a geometric series, we love a p-series, because they're very quick to test. And we'll actually talk about that in the next section when we start talking about comparison tests. But there we have a convergent p-series, which is great. Take a look at one more example of the integral test before we move on. I want to determine whether or not the given series is convergent. Here I have the sum from n equals 1 to infinity of e to the 1 over n squared, all divided by n cubed. So we say, okay, first thing I want to do is model this by a function of continuous variable x. So that would be e to the 1 over x squared power, all divided by x cubed. And from here, I want to think about this on the interval from 1 to infinity, the continuous interval on x. We say, well, let's see if we can argue these conditions. Is it positive? Well, I'm only taking x values from where x is positive. So x squared is positive, so I have e to something that's positive, which is going to give me something positive. And then divided by x cubed is positive since x is positive. So I have something positive divided by something positive. So we could make a similar argument to what we did earlier, saying here I have the quotient of positive things is going to give me something positive out, right? So it is positive on the interval. Is it continuous? Well, e is continuous, so I'm really looking at the nested function here, the exponent. We'll say, well, the only issue with this is division by 0. And overall, I have another potential for division by 0, and that would happen if x were 0. Then 1 over x squared would be a division by 0, and then e to the division by 0 divided by 0 would be an extra division by 0 to add more sort of chaos to the mix. But I'm not letting x be 0. It starts at 1 and goes on from there. So issue avoided, right? Now I need to know, is the function decreasing? And for this, I don't like to mess around. I would always encourage you to take a look at the derivative. So let me go here with f of x. Let me actually rewrite it. You could use quotient rule, but let me write it this way. E to the, instead of 1 over x squared, I'm going to say x to the power of minus 2. And instead of divided by x cubed, I'm going to say times x to the minus 3. And now I can work with product rule with a bit of chain rule to find f prime of x. So I'll say, let me rewrite e to the x to the minus 2 times the derivative of x to the minus 3 is minus 3x to the minus 4. And I can add to this. Now I'm going to rewrite x to the minus 3 times the derivative of my exponential function. the derivative of e to the stuff, and this is where I need chain rule, the outer derivative, the derivative of e to the stuff is just e to the stuff. But then I have to remember to multiply by the derivative of the exponent. And the derivative of x to the minus 2 gives me minus 2x to the minus 3. And I can clean up my derivative. Here, if I want to factor this e to the x to the minus 2 out, I'm left with negative 3x to the minus 4, or that's negative 3 over x to the 4th, plus I'm left with x to the minus 3 times negative 2x to the minus 3, so that's negative 2, and then x to the minus 6, or negative 2 over x to the 6th power. And I want you to notice that both of these terms here are negative. In fact, if I want to factor a minus sign out, I can do that. I can be very sort of deliberate with this and say this is negative 1 times e to the 1 over x squared times, and I brought the minus sign out, so just 3 over x to the 4th plus 2 over x to the 6th. Think about what you're plugging in. You're plugging in values on the interval from 1 to infinity. So this is going to be positive, this is going to be positive, the sum is going to be positive, times something positive, bam, multiplied by a negative 1. F prime of x is negative, which is telling me right away with no ambiguity that f of x is decreasing on that interval from 1 to infinity. I have a decreasing function. I'm happy to say that right now. So is it positive? You bet. Is it continuous on the interval? You bet. Is it decreasing on the interval? We got it. Since all three of these conditions are true, I can do integral test. So that's what we want to look at now. So now we move on to the integral test. We say, well, let's look at the integral from 1 to infinity of e to the 1 over x squared all divided by x cubed with respect to x. Improper integrals should not stay improper. First thing I want to do is write it as the limit as b goes to infinity of the integral from 1 to b of e to the 1 over x squared all divided by x cubed dx. Now I'm going to have to integrate this, and really whatever you need to integrate is whatever you need to integrate. For this one, it looks like another u sub, if you haven't noticed already. But speaking of noticing things, I'm going to use my favorite word here, notice. Notice, and we're going to look at just the generic improper integral for e to the 1 over x squared all over x cubed. I'm going to use the result to help out here. This is going to be a substitution. I'm going to let u be 1 over x squared. If I take the derivative, think of this like x to the minus 2. The derivative gives me minus 2x to the minus 3, or negative 2 over x cubed dx. And I can see this divided by x cubed in my original integral. I just don't have this negative 2. So I'd say we'll multiply both sides by negative 1/2. Negative 1/2 du is 1 over x cubed dx. And if it helps, you could even rewrite this integral as the integral of e to the 1 over x squared times 1 over x cubed dx. So you can see the parts a bit better. So this is going to become the integral of negative 1/2 times e to the u du. And we can integrate this without hesitation. We get negative 1/2 e to the u plus c, and then we would back substitute. We would say, what was u? U was 1 over x squared, so negative 1/2 e to the 1 over x squared plus c. And I don't need the constant since I'm planning on using this with a bounded integral, but here's all of my work to show the integration. And now I can say, well, this is convenient because I'm trying to integrate this function. And I want to take a look at the limit as b goes to infinity from 1 to b. So we'll say limit as b goes to infinity, but I've integrated here, so let me just pop this result in, negative 1/2 e to the 1 over x squared, and that's from 1 to b. And now I want to work through the evaluation. So still limit as b goes to infinity. I'm going to leave negative 1/2 factored out. You can leave it attached. It doesn't make a difference. I'm just not willing to babysit it right now. When I plug b in for x, I get e to the 1 over b squared. Minus, when I plug 1 in for x, I get e to the 1 over 1 squared. And I could go a little bit further with this before talking about the limit. Not much, though. Limit as b goes to infinity. negative 1/2 quantity e to the 1 over b squared minus, here I have e to the 1 over 1, which is e to the first, which is just classic e. But now I'm ready to talk about the limit. Now let me sort of make some note here in the margin so I can sort of show what I'm talking about. The only term that has a b in it is this 1 over b squared. So we'll say, okay, the limit as b goes to infinity of 1 over b squared, well, we'd say if b goes to infinity, then b squared goes to infinity. But look at where it is. Placement is everything. 1 divided by something that's going to infinity. If I have a constant and it's divided by something headed to infinity, that's going to 0. So here that limit is going to give me 0. So if I keep that sort of in mind, I'll say, okay, well, let me take the limit now. I have negative 1/2, and then here in the parentheses, I have e to the 0 minus e. We know e to the 0 is just 1, so negative 1/2, we got 1 minus e. And this is just a number. This is some constant, some finite number. So what this means is the improper integral is convergent. So then the same thing, the same result can be said of the series. So then the sum from n equals 1 to infinity of, it was e to the 1 over n squared all divided by n cubed, is also convergent by, and you can use hashtags, but I'm just going to write by integral test, whatever you like. But just make sure you're giving a shout out to the test that you're using. Integral test. There's some work that goes into it. It's not the fastest test, but I like it maybe even the most. Let's take a look at 11.4. We'll talk about the comparison tests, and there's 2 of them. 2 comparison tests in this section. We have the comparison test and the limit comparison test. And something that I like to do to help sort of keep the ideas a bit separate for students is I actually refer to the comparison test as the direct comparison test. And that's just something that I do. Let me know in the comments if you like that idea or if you don't like that idea. But when you say, I want to do a comparison test, the question is, well, which one? There's 2 of them. Do you mean limit comparison test, or do you mean classic, original recipe comparison test? Which is why I usually call this the direct comparison test. And then what does it say? It says, suppose the sum of a sub n and the sum of b sub n are series with positive terms. If the sum of b sub n is convergent and a sub n is less than or equal to b sub n for all n, then the sum of a sub n is also convergent. Or, if the sum of b sub n is divergent and a sub n is greater than or equal to b sub n for all n, then the sum of a sub n is also divergent. Face box out of the way. These are 2 of 4 possibilities. So the comparison test, aka the direct comparison test, won't always give us information. And I want you to think of it this way. If I have a series that is convergent, and then I have a series that I know is smaller than it, well, it can't diverge. It's smaller than something that's converging, so there's no way for it to like head off to infinity. So we'd say, well, if I have a known series that is convergent, and then a smaller series that I'm trying to figure out what's going on with it, that smaller series must also converge. Or, the other thing that the comparison test is saying here is if I have a series that I know diverges to infinity, and there's another series that's larger than this, well, that larger series, there's no way for it to converge, it must also diverge. So, smaller than convergent is convergent, larger than divergent is divergent, but there leaves me 2 other possibilities that are inconclusive. Let's say I have something that's convergent, and I have something that's bigger. That bigger series, it could converge to something larger, or it could diverge. I don't know. I wouldn't be able to tell you. Or, let's say I have a series that is divergent, and I have something that's smaller. That smaller series could converge, or it could still diverge, just diverging a bit slower, we would say. a bit less dramatic with its divergent than the other one. So we really have to be careful with this direct comparison test. If it isn't set up to perfectly give us a conclusion, don't pretend like it's giving you a conclusion. Be very honest about what your discovery is. If the direct comparison test doesn't work, then we have the limit comparison test. I love the limit comparison test. This is a good day for me because I love a lot of the stuff we're talking about. Suppose the sum of a sub n and sum of b sub n are series with positive terms. If the limit as n goes to infinity of a sub n divided by b sub n is equal to some number c, where c is a finite number and c is greater than 0, c for Corey, then either both series converge or both series diverge. So we're trying to sort of pick a series to compare with to do the limit comparison test where we can, know what the result is going to be. And that's true of both of these. But let's talk about the comparison tests. Determine whether the series converges or diverges. Here I have the sum from n equals 1 to infinity of n divided by 4n cubed plus 1. Well, okay, so let me just find a quick comparison here. And it's always going to be quick and easy to ditch some constant that we're either adding or subtracting. So I'm going to just get rid of this plus 1 and compare this against n over 4n cubed. Now the question is, which is bigger, which is smaller? On the left side, I have a bigger denominator. Bigger denominator means smaller fraction. If you're not sure, if you're just not sure, pick a test value. Say, what happens when n is equal to 1? If I plug 1 in here, I'm going to get 1 over 4 plus 1, that's 1/5. Over here, I'm going to have 1 over 4 times 1, which is 1 over 4, which is smaller. 1/5 is smaller than 1/4. So that can help me, but I think it's also a good habit to just getting comfortable looking at these and saying, okay, bigger denominator, smaller fraction. Smaller denominator, bigger fraction. Some argument like that. But here, this n over 4n cubed, I can simplify it. I didn't yet, but I'm going to. That's a 1 over 4n squared. And now let's think about these as series. Since term-wise, and I want you to notice these are series with only positive terms, so it's worth mentioning that as a condition of the comparison test. I'll say if I think about this, the sum from n equals 1 to infinity of n over 4n cubed plus 1 should be, in some regards, smaller than the sum from n equals 1 to infinity of 1 over 4n squared. If these things both head to infinity, then it's kind of difficult to make a claim quite like this. But what's happening, if I look at this other one here, we'd say, well, this is nice. This is a p series. It has a coefficient of 1/4, but otherwise, it's a p series. I could write it as 1/4, the sum from n equals 1 to infinity of 1 over n squared, if that feels better. The p series with p equals 2, which is greater than 1, which is a convergent p series. And this is larger than what I was given originally. So this is smaller, the smaller series will also converge. And that's by the direct comparison test. Give a shout out to the test you're using. By direct comparison test. Take a look at another example. Determine whether the series converges or diverges. Here we have the sum from n equals 1 to infinity of n cubed over 2n to the 4th minus 1. So I'm just going to pop this out for a bit. N cubed over 2n to the 4th minus 1. And I can quickly compare this to, let me just ditch the minus 1. That's a fast move I can make where I should be able to place an inequality sign in between these. I'll say over here on the left, smaller denominator, bigger fraction. And again, if you're just not sure, do a test value. What happens when n is 1, for example? Here I get 1 over 2 minus 1, which is 1 over 1, which is 1. Here I get 1 over 2 times 1, which is 1 over 2. So, well, 1 is greater than 1/2, so I can just sort of check myself a little bit before I wreck myself. But then I can simplify this new series that I'm comparing with. I can say, well, this reduces to 1 over 2n, or 1/2 times 1 over n. And now let's bring in the summation notation. The sum from n equals 1 to infinity of n cubed over 2n to the 4th minus 1 should be, we can sort of say this with relative certainty, it should be greater than the sum from n equals 1 to infinity of 1 over 2n. Term-wise, it's true. Term by term, move by move, bit by bit. But what is this? This is also a p-series with p equals 1. And again, you can bring that coefficient out if it's bothering you. Say 1/2 sum from n equals 1 to infinity of 1 over n. It's a p-series with p equals 1, which is divergent. Where this is also, if you're sort of, yelling at your computer screen right now, it's the harmonic series, which is a known divergent series. You could either argue as a p-series or harmonic series, whatever you'd like. This is divergent. What I have is larger term-wise than something that diverges. So this must also diverge. So we'll say the larger series will also diverge. And the reason why I have this in quotations, I just want to be careful about comparing infinities, right? This isn't really sort of, an argument that we're trying to get into. We're just trying to say that term-wise, bit by bit, these are going to have larger terms. So if this one is diverging, then the quote-unquote larger one will also diverge. Seems reasonable to say. So larger series will also diverge by the direct comparison test. So we got a divergent series here with that direct comparison test. And this is a great test because of how quick it is. Let's see one more. So here I have sum from n equals 1 to infinity of 9 to the n over 2 plus 13 to the n. Let me just pop it out for a bit. And I'm going to get rid of this 2 that I'm adding. It's a quick move that I can make, and I should be able to compare these. Bigger denominator, smaller fraction. And you can always, plug in values and do that to help out. But once we get that inequality, we're good. And here, I can actually collect this a bit differently. I could say, since they both have that exponent of n, 9 over 13 all to the power of n. And let's bring in the series notation, the summation notation. Sum from n equals 1 to infinity of 9 to the n over 2 plus 13 to the n should be less than the sum from n equals 1 to infinity of 9 over 13 all to the n. Now, what do I know about this? This isn't quite in the exact form it should be in, but this is a geometric series. We can probably see that right away. Since it's starting at n equals 1, it should be the form, sum from n equals 1 to infinity of ar to the n minus 1. So if I really wanted to modify this perfectly, I would actually bring out a 9 over 13 and say, okay, this is really 9 over 13 times 9 over 13 to the n minus 1. We see a is 9 over 13, r is 9 over 13, but it's really just the value for r that we're looking at. And we'd say, since this is a proper fraction, since r is between -1 and 1, this is a convergent geometric series. So I have a convergent geometric series. Now, the one that I really want to talk about, got this cat back here, waking up from a cat nap, ready to do some Calc 2 with us. The smaller series, then, must also converge. So the smaller series will also converge, and that's by the direct comparison test. The direct comparison test is really fast. We like to compare with p-series and geometric series because those give us quick results. What about when I can't quite do that? So here I have something, I have the sum from n equals 1 to infinity, 5 plus 7 to the n over 5 plus 6 to the n. And I could get rid of the 5 on top and bottom. It's difficult, though, to really get a good feel as to how that inequality should face. Could I try to mess around with that? Sure. Would it take a lot of time? Probably, and it's not really what I want to be doing. So let me just consider this to be my a sub n that I'm starting with. I want to now consider the limit comparison test instead. Let's go back and see what the limit comparison test said, and then we'll take a look at some examples of it. Limit comparison test says, suppose that the sum of a sub n and the sum of b sub n are series with positive terms. If the limit as n goes to infinity of a sub n divided by b sub n is equal to c, where c is a finite number and c is greater than 0, then either both series will converge or diverge. So they both behave the same way. And it doesn't really matter which is a sub n and which is b sub n. That's arbitrary. So if you flip that ratio, it doesn't make a difference, really. What I want to do is I want to compare this against another series b sub n. How should the generating term for b sub n look? I'm going to ditch the 5s, and I'm just going to look at 7 to the n over 6 to the n. Which, if I want to collect it, I could say 7 over 6 all to the n, but I'm going to use this version of it. And now, with limit comparison test, I want to look at the limit as n goes to infinity of a sub n divided by b sub n, where this is the limit as n goes to infinity of, I have a sub n on top, which is 5 plus 7 to the n over 5 plus 6 to the n, and then divided by b sub n, which is 7 to the n over 6 to the n. And I don't want to divide a fraction by a fraction, so instead I want to flip this and multiply. We'll say limit as n goes to infinity of 5 plus 7 to the n over 5 plus 6 to the n times, if I flip this, I have 6 to the n on top over 7 to the n on bottom. And I want to use the old swap 'em denominator trick. So I'll say this is the same as the limit as n goes to infinity of, I'm going to leave the 5 plus 7 to the n on top here. And what I'm going to do is I'm going to take the 7 to the n in the bottom and the 5 plus 6 to the n on the bottom, and I'm going to switch these. And I can do it since I'm multiplying everything. So here I'm going to have 7 to the n in the bottom here, times, here I have 6 to the n on top. But then now in the bottom, I'm going to move that, shuffle that 5 plus 6 to the n over there. So I've just sort of rearranged this, right? We know we could do that with multiplying, so it's not a big deal. But this is going to help me out a bit. Now, with this first fraction, I can actually just break up the numerator, which is always a nice move to make if we can. So that's going to be 5 over 7 to the n plus 7 to the n over 7 to the n. But then here, I can't break up a denominator. We have a similar trick that we would use. We would divide everything by 6 to the n from the denominator. So I would do 6 to the n over 6 to the n divided by 5 over 6 to the n plus 6 to the n over 6 to the n. And then I would reduce these where I can. So we'll say limit as n still goes to infinity. I have 5 over 7 to the n and then plus 1 times, and here I have 1 on top, divided by 5 over 6 to the n and then plus 1. And now I can take a look at my limit as n goes to infinity. Now as n goes to infinity, 7 to the power of n goes to infinity as well. 5 divided by something going to infinity is going to give me 0. And then here in the other one, I have 1 on top. Same argument. We'd say 6 to the n goes to infinity as n goes to infinity. 5 over 6 to the n goes to 0. So I get 0 plus 1 times 1 over 0 plus 1, which is going to give me 1 times 1, which is 1. And this is that value that we're calling c. And we can say since c is positive and finite, either both series are going to converge or both are going to diverge. Let's figure out what's going to happen. Now, the one that we're starting with, I don't know. If I knew what was going on with it, I would have said it already. But let's look at b sub n. 7 to the n divided by 6 to the n. Sum from n equals 1 to infinity, 7 to the n over 6 to the n, which we said we can write that as the sum from n equals 1 to infinity of 7 over 6, all to the power of n, which is a geometric series, and you can probably see if it converges or diverges right away. But just to make sure it looks properly like one, I'm going to bring out a 7 over 6. So I have that a and then r to the n minus 1 form that I need if my series is starting at 1 for the starting index. Let me say this is a geometric series with r equals 7 over 6. And that means this is too large, right? So the absolute value of r needs to be less than 1. It's not in this case. So this is a divergent geometric series. Now with limit comparison test, we're saying both series behave the same way. Since my comparison series in limit comparison test is divergent, this means our original series, which was the sum from n equals 1 to infinity of 5 plus 7 to the n over 5 plus 6 to the n, is also divergent. And that's by limit comparison test. By the limit comparison test. We always want to mention the test that we're using to justify this. And let's see one more example of this limit comparison test in action. Here I have the sum from n equals 1 to infinity. We have square root of n plus 2 on top, divided by 3n squared plus n plus 4 on bottom. And what I'm starting with, I'm just going to consider that a sub n. A sub n is this radical n plus 2, all divided by 3n squared plus n plus 4. Now for building this comparison series, b sub n, for building its generating term to start, what matters are leading terms, leading behaviors, coefficients, constants that we're adding. Those don't really make a difference. What matters is going to be the leading term. So the leading term on top is just this n to the 1/2 square root of n. So that's all I'm going to take away from that. Divided by, in the bottom, the leading term is an n squared term. I don't care about the 3. I don't care about you 3. N squared is what that leading term is. And this is what I want to compare with. This is what I want to compare with. So now I can set up for that limit. Limit as n goes to infinity. A sub n is on top. Radical n plus 2 over 3n squared plus n plus 4. And then divided by b sub n. So divided by radical n over n squared. And I don't want to leave this as a fraction divided by a fraction. So let's multiply by some reciprocals here. So numerator can stay the same. I think I started writing n squared, which I don't do. So radical n plus 2, I'm on my best behavior, over 3n squared plus n plus 4. And then multiplied by, now I'm going to flip this fraction on the bottom, so that's n squared over radical n. And let's do that denominator swap trick. So I'm going to keep radical n plus 2 on top, but then I'm going to bring radical n over. I'm going to trade it over, and then times. Here I have n squared on top. I'm going to bring this 3n squared plus n plus 4 over. And let's see if we can't start simplifying. Now this very first, I think of this as fraction times fraction, this first fraction, I have a radical on top, a radical on bottom. I can use the quotient property of the radical in reverse to write this all as 1 square root, n plus 2 all over n. Think about breaking that fraction up from there. And then over here, I'm going to use that famous trick, dividing by the highest power of n in the denominator. So divide everything by n squared. So that's n squared over n squared divided by 3n squared over n squared plus n over n squared plus 4 over n squared. And let's keep simplifying. Here to simplify this. Limit as n goes to infinity of square root of n over n. If I break this up, n over n gives me 1, plus 2 over n stays, times, and then here I have n squared over n squared is 1, divided by 3n squared over n squared is 3, plus n over n squared is 1 over n, plus 4 over n squared. Now I can talk about my limit as n goes to infinity. Any constant divided by n as n goes to infinity goes to 0. Constant divided by n squared as n goes to infinity gives me 0. So this is going to give me square root of 1 plus 0 times 1 over 3 plus 0 plus 0. And what does it look like? Well, I'm glad you asked. I have square root of 1 times 1/3, which is 1 times 1/3, which is 1/3, which is what I get for my value for c. And I want you to notice this fits the bill. This is finite and positive, which is what we're saying from our limit comparison test. Okay, that means both series are going to either converge or diverge. I just need to know which. Let's take a look at what we were comparing against, because the original series, I don't know. If I knew, I would have answered already. But we were comparing against the series for b sub n. And how did b sub n look? It was radical n over n squared. But I can simplify this. If I think of this radical n as n to the 1/2, this is going to give me 1 over n to the 3/2 power. If I just, subtract exponents and rewrite. This is a p series. With p equals 3/2, which is greater than 1. I think sometimes we refer to these as partial p series, but I just call it a p series. A p series with p something greater than 1, which means it is convergent. Which means that our series, which was the sum from n equals 1 to infinity of, oh gosh, what was it? It was square root of n plus 2 on top, something like that. And then 3n squared plus n plus 4 on the bottom is also convergent by the limit comparison test. So both are going to behave the same way. I compared it against something that's convergent, so this is going to converge as well too. Hey, thank you so much for spending your time with me, checking out some of these problems. If you're still here in the video, all I can do is say thanks. Thanks for your time. Go ahead, take a look at the homework. Let me know how you're doing with the material. Check in every once in a while. Keep me in the loop. But otherwise, no matter what you're doing, where you are, remember to always keep learning, keep dreaming, and to always follow your heart. And we will see you next time. Until then, take care.